Well, we all know how to balance chemical reactions, but there's another another subclass of balancing, or a special case of balancing chemical equations that needs to be introduced. It's not only balancing the atoms in the uh, chemical equation, but also balancing the charges, as in, say, perhaps when a transfer of electrons takes place, and that's called reduction and oxidation. If I take a piece of copper and put it into some silver water, silver ion containing water, silver nitrate, for example, the copper will actually give up electrons to the silver, and the copper metal becomes copper ions entering into solution, and the silver ion gains electrons, purifying itself into pure silver. If I look at the oxidation states, or oxidation numbers, of the copper and the silver, of course every element in their pure form is a zero oxidation state. So 0 for copper here and 0 for silver here. But as ions, the silver 1 plus and the copper 2 plus have those exact oxidation states. So one way I write it sometimes is I'll say copper goes to copper 2 plus, and that's a loss of 2 negative electrons. And silver plus goes to silver, pure silver, and that's a 0, and that's a gain of 1 negative electron. Gaining electrons is called a reduction. Losing electrons is called an oxidation. Not only that, as confusing as I've already made it, no, it's not my fault, I didn't do it, I'm just the messenger here. If copper gets oxidized, it's called the reducing agent. It helps someone else get reduced. Who did the copper reduce? It reduced the silver. The silver went from a 1 plus to a 0, so the silver got reduced. And similarly, if the silver ion got reduced, it's called the oxidizing agent. Indeed, if I touch silver nitrate water with my skin, the silver ion takes electrons from my skin, turning it kind of brown in the laboratory. Doesn't hurt any, but it sure doesn't look very pretty for a few days till that layer of skin wipes away. In any case, the balancing goes like this. If one copper loses 2 electrons and one silver gains 1 electron, I have to have 2 electrons lost and 2 electrons gained. So I'm going to multiply this whole thing by 2, that is this silver and this silver. And voila, I've balanced my chemical, my redox reaction by inspection, saying 1 copper, 1 copper, 1 silver, 1 silver, but I had to take 2 silvers because the 2 plus charge on the copper on the right has to balance the 2 plus charge on the left of the silver. So not only do the atoms have to balance, the charges have to balance, which seems confusing. Here's another one. In a similar way, take a pure piece of iron, clean iron, put it in some copper sulfate water. The iron loses electrons to the copper. The iron loses electrons to the copper ion. The copper ion, in a sense, grows as impure. No, I say impure, but it's impure because of all the aqueous junk floating around. But you see little copper wet crystals growing on that iron structure. Like take a paperclip, piece of iron, put it in some copper sulfate water. You see this interesting copper formation growing on that. So the iron here is a 0, the copper here is a 0. This copper 2 plus ion is a 2 plus oxidation state. This iron 3 plus ion is a 3 plus oxidation state. So from that, can you tell who gets reduced and who gets oxidized? Maybe you can. This copper 2 plus goes from a 2 plus to a copper 0, and the iron 0 goes from an iron 0 to a iron 3 plus ion. So this solid iron kind of gets lighter, less mass on this structure, and that iron atoms enter into solution as ions, having lost electrons to the copper. But if 2 electrons are gained by the copper from a 2 plus to a 0, and 3 electrons are lost by the iron, I have to make the 2 and the 3 match up somehow. Do you have any idea how we're going to do that? Because this equation is a balanced chemical equation, but not really, because it doesn't balance the charge. The 2 plus on the left and 3 plus on the right don't jive. In any case, you know where I'm going with this probably. If iron gets oxidized, it's called the reducing agent. If copper ion gets reduced, yeah, it did. Got to be careful how you say this. Gets reduced from a 2 plus to a 0, it's the oxidizing agent. So how do you make the 3 lost and 2 gained match up? Take this and this times 3, and take this and this times 2, 2, right. And there's the balanced redox reaction. 2 irons and 3 copper ions react to become, sorry about that, 2 iron 3 plus ions and 3 copper atoms. Interesting. Here's another one, very similar. Here I started out with a chlorine molecule which has 2 chlorine atoms. Chlorine is still in the 0 oxidation state as a gas, but over here the chloride ion is a -1 ion, so it's a -1 oxidation state. Pure aluminum is a 0 oxidation number, but the aluminum 3 plus is a 3 plus. Aluminum 3 plus ion aqueous is a 3 plus oxidation state. So here I have 2 chlorines, and I figured I better get 2 chlorines over here, and thinking about each of those 2 chlorines become a chloride -1 ion, I said each of 2 chlorine atoms gains an electron, so that's a reduction, gaining negative electrons. So that's 2 electrons gained, and this is 3 electrons lost. You might already guess how you're going to make that match up. You can figure out the agents there, can't you? Like, is this the oxidizing agent or is this the oxidizing agent? You should do that, shouldn't you? Yeah, you should. Anyways, take this whole mess times 3. 3 times 2 is 6. And take this aluminum and this aluminum 3 plus ion, take that times 3, and look something like this. So the bottom line is something like this. Yeah. I wish I could ask you if you had any questions, but I'm talking to my computer right now. This is not interactive. I apologize. Modern times, what do you do? Here's another one if we care to look at another one of this type, aluminum. Oh, this is kind of good, because aluminum goes to aluminum chloride aqueous, and HCl, hydrochloric acid, if it's concentrated acid, can do this reaction to make hydrogen gas. Looking at the oxidation states, this aluminum pure metal goes to aluminum 3 plus, and the hydrogen stays as, oh no, it doesn't stay. The hydrogen is a +1 ion here in the HCl, and it goes to pure hydrogen gas. Looks like the chlorine doesn't change from a -1 to a -1 here. Yes. Oh, I was trying to balance the atoms. Noticing 3 chlorines here and 1 chlorine here, I thought originally, well, maybe I'll just put a 3 here. That'll give me 3 chlorines and 3 chlorines, but if I did that, that would give me 3 hydrogens. That would never balance this even number of hydrogens without putting some other even number in front here. So I bumped it up. I said, let's take 6 of these and 3 of these. That balances my hydrogens. And that's 6 chlorines, and 2 times 3 is 6 chlorines, and that gave me 2 aluminums and 2 aluminums. Voila, it's balanced, yeah? I think it is. We better check the oxidation states though. So aluminum, each of 2, now I had 2 aluminums here, each of 2 aluminums lost 3 electrons, so that'd be a total loss of 6 electrons. And each of 6 hydrogens gains 1 electron to go from a 1 plus to a 0, and that's a gain of 6 hydrogens, so that looks pretty good too. That molecular type equation, as I wrote it up here, didn't mention the charges and or oxidation states, but if it was written as an anionic equation, then I suppose you'd want to look at those charges. Oh Lord, there's more. Yikes. This one's fun. This is a classic. Iron 2 plus gets oxidized to iron 3 plus by the permanganate ion. It helps to have some H plus acid in there, extra H plus. Iron 2 plus, iron 3 plus, that's an oxidation. Yeah, losing 1 negative electron. This one's not quite so obvious. The manganese here you can figure out as a +7 charge. You should be able to figure that out. It goes to a 2 plus charge over here. Right, so manganese 7 plus to 2 plus, that's a gaining of 5 electrons. And here, this iron 2 plus to iron 3 plus is a loss of 1 electron. So what should I multiply these irons by in order to allow the transfer of electrons to balance out? You know the answer. Oh, I forgot to mention up here at this point, I noticed that on the left-hand side I had 4 oxygens, and on the right-hand side I had oxygen in only one place in the form of water. So I decided to put a 4 here to get 4 oxygens. Putting a 4 here gives me 8 hydrogens, so I put an 8 here. That balances the atoms, but then I proceeded to balance the charges by sticking a 5 in front of the iron 2 plus and a 5 in front of the iron 3 plus, and we could check it. Should we check it? We better check it. Let's see. Oh Lord, what a mess. 5 times 2 is 10 plus, 8 times 1 is 18 plus, and 1 minus is 17 plus on the left hand side of the arrow. Do I also have a 17 plus on the right hand side? Did I do my math correctly? 5 times 3 is 15 plus, 16, 17 plus. Oh yay, I got it right. So I have 17 pluses on the right and 17 pluses on the left, and the charges balance in addition to the atoms balancing. That's why I need the 5 in front here and the 5 in front here. Pretty tricky. Are you getting tired of this yet? I am. I need a drink of water. Okay, one more, and I'll stop. There's more, but you can look at it at your leisure if you want to. Iodide ion, water, permanganate. Iodine molecule, manganese dioxide, hydroxide. Oh goodness, that's interesting. Again, the manganese 7 plus here goes to manganese 4 plus here. You should be able to figure out those oxidation states of those manganese atoms in those oxide species. This iodide goes from a -1 to a 0. So I put a 2 here in front of the iodide ion because they have 2 iodine atoms over here in a molecule. And so each of these 2 iodine ions loses a negative electron to become an iodine atom in a molecule. And that's a gain of 3 electrons from a 7 plus to a 4 plus for the manganese. How do you make 3 electrons gained and 2 electrons lost match up? You know the trick by now. There's another way to do this. We look at it in Gen Chem 2, but this is called balancing the redox equation by inspection. In any case, I took this mess, iodide and iodine times 3. I took the permanganate and the manganese dioxide species times 2 to get 2 and 2 and 3, and 3 times 2 is 6. Then I could go through and check. I should have 6 iodines and 6 iodines and 2 manganese and 2 manganese and 8 hydrogens and 8 hydrogens and oh goodness, 8 oxygens here plus 4 more for a total of 12 oxygens, and 4 times 2 is 8 oxygens plus 4 more oxygens is also 8 oxygens. So the masses balance out to the charges balance. On the right hand side I have no charge, 8 times -1 is -1 charge on the right of the arrow. On the left of the arrow I have 2 negatives and 6 negatives for a total of 8 negatives. Interesting, it works. Well, if you have no idea what I just said, why don't you try this one? And the answer is given to you there as well. Is that the only other one I'm not going to go over? I think it is. Yeah. That's just chicken scratch. You can ignore that one. I might not put that on the PDF. Anyway, there's another example there if you feel like looking at it. This is called the balancing a redox reaction by inspection. It's not easy. There's a different way that I think is easier, but it's more involved. And bottom line is if you can do something simple like the first one, oops, went too fast. Like the first one I started with up here, like this copper and silver, or even a little bit more complicated would be the iron and the copper 2 plus. That's a pretty good one to be able to do, something like that. This one's pushing it. But we're just looking for, the fundamental ideas of balancing not only the atoms, but also the charges on both sides of the arrow. Have to balance. Guys, gosh, thanks for watching. I'll see you in class, eh?